Hello everyone, my name is Gleirscher, and together with Simon Foster, we will present work in progress on deductive verification of control algorithms for autonomous marine vehicles. Such vehicles are special in that they combine discrete event control with continuous evolution of the physical parameters that constitute them. The gold standard for modeling and reasoning about such systems is the theory of hybrid systems. This theory is well applicable and has been applied very often to many kinds of cyber-physical systems and their autonomous specimens. A typical challenge, recent challenge, is to bring modern hybrid system verification techniques to control practitioners. These practitioners today typically employ mathematical software such as MATLAB, Mathematica, and Modelica to develop their controllers. And there is a gap still existing between established packages for numerical computation and computer algebra systems and modern hybrid verification tools such as Chimera X and Isabelle Hall. Therefore, our research goal was to develop a workflow that links, in our case, a numerical computation system. We use the GNU Octave system, an alternative for MATLAB, with a deductive theorem prover. In our case, a theorem prover, special proof assistant built on top of Isabelle Hall. As a case study, we use the autonomous marine vehicle Seaworker 5, developed by ASV Global and used for hydrographic survey work. The company D-Risk developed a verified safety controller for this system called the Last Response Engine. The purpose and responsibility of the Last Response Engine is to respond to certain critical events and to direct corresponding control input to an autopilot, which is responsible for the usual navigation of the AMV. In a particular mode, a human operator can also forward or request manual control of the AP. Now, the central question is, how do we provide assurance for the whole system, including the autopilot, the continuous dynamics, the LRE, by means of verification and model validation in a combined way. Our preliminary results include an overall model of the AMV control system crafted in GNU Octave, containing the dynamics of the AMV, the behavior of the autopilot controller, and the behavior of the safety controller. We use a small generic simulator to validate this model for several scenarios. For formal verification, we use an extended differential Hall logic prover built on top of Isabelle Hall. We translate our Octave model into a hybrid program usable by this prover in order to verify certain properties of the AMV, that within Isabelle Hall. Let me now explain to you how we model the system in Octave. To model the AMV dynamics, we consider the parameters such as position and velocity vectors, the mass of the AMV, a nearest obstacle, and the location of the next waypoint. All vectors. As the main control input, we consider as an abstraction of the thrusters mounted at the AMV a propulsive force comprising two components, a longitudinal force and a transversal force. From this force, we can, according to particle dynamics, derive the acceleration, V A dot, and in turn, the movement P A dot of the AMV. The discrete event behavior of the last response engine is modeled as a hybrid automaton. This automaton has several modes: a main operating mode, where the last response engine is responsible for detecting or monitoring at runtime certain critical events, an operator control mode where the last response engine is idle and where inputs to the autopilot are given by the operator. In case the AMV gets near an obstacle, the last response engine switches into a high caution mode. Near obstacle is defined by the distance between the AMV and the nearest obstacle being smaller or less than a safe braking distance. In case the AMV is getting on collision course, the LRE switches into a collision avoidance mode, where, in addition to being near the obstacle, the AMV's velocity vector is supposed to point towards the obstacle, which means the angle between the velocity vector of the AMV and the obstacle is below a threshold epsilon phi. The difference between HCM and CAM modes is that the LRE instructs the autopilot in HCM mode to switch to a safe speed. And in addition to that, in CAM mode, the LRE switches the autopilot into a mode where the transversal force is calculated in a way such that the obstacle is circumvented. We converted that model, that hybrid automaton, into an Octave script. On top, you can see the switching logic embedded in the first function here. The result of the controller is the calculation of the force of the propulsive force vector. That function is embedded into a control loop function, which combines the controller with the dynamics of the MV, ending up with a calculation of the state update x dot. We use an extra function to simulate this, the controller and the loop, by using a numerical solver for ordinary differential equations. And in order to validate our model, we visualize this whole model. And in the graph on the top left of this figure, you can see the AMV as a green dot, the next waypoint as a blue dot, the nearest obstacle as a pink dot. We allow in the simulator the obstacle to move, whereas for the sake of simplicity of the verification, we assume the obstacle to be static. Here you can see by walking along the trajectory, when the AMV approaches the obstacle, you can see it deviates a little bit from the otherwise smooth trajectory in order to circumvent the obstacle. Surrounding that bigger graph, the visualization of the trajectory, the simulator allows validation also in terms of the development of the parameters of the model. For instance, the generation of the propulsive force here in the top right corner. I'd like now to hand over to Simon Foster, who will explain how we translated that model into Isabelle DH, or proof assistant, and how we verified certain properties. Simon, please.
Thank you, Mario. Yeah, so what we did once we'd crafted the model in Octave was to convert it into a notation called hybrid programs, which is basically derived from Platzer's differential dynamic logic, but embedded in Isabelle Hall, and then applied a verification technique to it called differential Hall logic that we've developed previously. So just to give you an idea of how this works, a hybrid program indicated at the top there consists of two parts. There's a controller, which is written in an imperative programming notation and describes discrete updates to the system responding to continuous stimuli. And then secondly, you have the dynamics. And this is written as a guarded first order system of ordinary differential equations. And basically the idea here is that we only admit solutions where the invariant B holds throughout, right? So B is a kind of boundary condition. So just as an example of this, we have, if we go on to the next one, a simple speed controller And the idea of this controller is that it's going to try and maintain a velocity of around 70. Of course, it's very simple, so it wouldn't really work that well in practice. But what happens is the controller, the first part there towards the left of the sequential composition, it says if the velocity is greater than 0, then it's going to apply a braking force by setting the acceleration to minus 0.1. Otherwise, it's going to set the acceleration to 1, so it's going to get faster. The dynamics is given by an ODE over two continuous variables, velocity v, the derivative that's a, and then the derivative of a is 0. So the acceleration is only changed by the controller. And then the boundary condition is that v must remain between 0 and 75 because the dynamics can, in theory, continue to evolve indefinitely, and so the boundary condition ensures that it must at some point give over control. So you've kind of got a game going backwards and forwards between the controller taking turns to update the variables and the dynamics taking turns, indicated by the Calinescu star operator there. So it's iterative, it goes backwards and forwards. Okay, then on to the next. So then to verify this, you'll see that the Hoare triple notation has now appeared at the top. Now the Hoare triples here are slightly different to your traditional Hoare triples because they're not talking about pre and post conditions. They're talking about preconditions and an invariant over every run of the continuous variables, right? A system level invariant, right? So what we do is, so to prove this, we need to find two invariants, I1 and I2, such that I1 is an invariant of the controller and I2 is an invariant of the dynamics. And then we need to show that the precondition satisfies the composition of the two invariants. I'm using composition in a loose way here because they kind of get convoluted in some way because we kind of have sharing of variables between the controller and the dynamics, and you have to show that the two invariants imply the overall system environment you want to show. So then the way that we prove this is we can use standard imperative Hoare logic reasoning to prove the first one, and we use a technique called differential induction to prove the second one. So this is a technique from differential dynamic logic where you can prove an invariant of an ODE without needing a solution. Basically, so it's a very powerful technique and highly automated. We also have a kind of separation like logic like reasoning for ownership of variables, so the controller can own certain variables, the dynamics can own certain other variables, and that allows us to split proof into modular parts. So the next slide, please. So then we can model the AMV using a sequential composition of three components: the last response engine, the autopilot, and the system of ODEs. I'm just going to show you one of these because for the sake of time, but the ordinary differential equation. So here we're using the Isabelle notation for this example. So we have 6 continuous variables. We have the position, the velocity, and the acceleration, which are all given their sort of standard Newtonian interpretations. So if you just show the first bullet, you'll see that. And then you have the next one, please. You have the derivative of the heading, which is given by the angular velocity. And the angular velocity is calculated using the arc-cos function, which is, of course, transcendental. And this shows us one of the benefits of using Isabelle, because we can reason about transcendental functions, and we can also reason about things like vectors, as I'll mention in a moment. The linear, sorry, I'll just say that. So V and A here, they're both vector quantities, not scalar quantities, but we can still write them down in a very simple and intuitive way in Isabelle. And then next one, please. So then we have this evolution constraint, and you'll see that we have this like vector notation that we've added to Isabelle, and this is to kind of try and shrink the gap between the model that we have in Isabelle and what we have in Octave. And the evolution constraint in this case, so this is a property that holds throughout continuous evolution, and it says that the velocity vector can be calculated by multiplying the linear speed s by the orientation vector, and the orientation vector is calculated by using sine and cosine. So again, two transcendental functions in this kind of matrix notation. Okay, and so then what we can then do is, so once we've composed the AMV of the three parts, again, the LRE, the autopilot, and the dynamics, we've then got a number of proof tactics in Isabelle Whole that we can use to verify properties. So we have a tactic called HORE-WP Auto, and this is used. This uses weakest precondition calculus to prove normal Hoare logic conjectures. So using a kind of standard technique for Hoare logic reasoning and using the standard rules of Hoare logic. Secondly, we have a tactic which we've developed called Deduct, and this proves differential invariance. It automates calculation of Lie derivatives, and then it discharges, and then it produces a set of verification conditions for your differential invariant with respect to your dynamical system, and produces a set of verification conditions that need potentially to be discharged, perhaps using automated theorem proving or SMT solving, or Isabelle's got a variety of facilities to deal with that. Or there may be no verification conditions, which can also be the case. And also, as I mentioned, we support modular verification, whereby we can prove invariance of individual components of a system and then put them together and lift invariance to the system level. So I'll now just to conclude show a couple of examples of theorems that we proved in Isabelle DH. So the first one is a property of the autopilot, and it's telling us that if the AMV is close to the set point speed, so the set point speed there is the difference between the requested speed RS and the actual speed S, and if this is less than or equal to S epsilon, and the requested heading is where we want to be going, then the autopilot isn't going to do anything. It's not going to change the acceleration because we're already on the correct course. And this property can be proved using the HORE-WP auto tactic. The second property is a property of the LRE itself. And so this is showing a property of the kind of hybrid automaton that we saw. And what it's saying is that if the LRE is in main operating mode and an obstacle is close, meaning that there's an obstacle present in the obstacle register, so that our position is getting close to that obstacle, then we're going to transition to high caution mode, right? And that's encoded using a Hoare triple again. And the final property is then a property of the dynamics. And what it says is if the acceleration is 0 and the AMV is moving, then the heading is not going to change. And you can see that because phi, you've got phi equals x in the precondition and in the postcondition, which means it's constant, as you'd expect. So if the acceleration, if no propulsive force is being applied, and so the acceleration is 0, then the AMV is just going to continue going in a straight line. Now that is that property is proved using the Deduct tactic, although it's actually a slight extension called Deduct Mega, which also applies some additional reasoning in Isabelle to make the reasoning more automated, and therefore there are no verification conditions in this case. Good. So I'm just going to conclude now. So what have we done? So our initial study, I think, shows that we can have effective cooperation between numerical computation systems like Octave and interactive theorem proving on the other hand. We need to extend those ITP libraries sometimes to provide the full range of operators available in languages like Octave and MATLAB. But on the whole, most of those operators are available within Isabelle. The experience there has been very good. We think maintaining traceability between the two notations is very important, and that's why we've tried to extend the Isabelle notation so that we can have things like vectors and so on written in an intuitive way. And Isabelle supports us in this way because it provides a very flexible system for writing notations, and also a lot of automated proof facilities we're able to make use of that are provided by the whole analysis library and also the archive of formal proofs. So then in future work, our current models of the LRE and autopilot in Isabelle are simplified, and that's just for the sake of time constraints. We want to further develop those in the future. We also want to prove more substantial invariance related to collision avoidance. So at the moment, the properties are quite simple, and so we want to put those into a bigger context. We also would like to automate the transformation between Octave and hybrid programs and support more complex dynamics. We can potentially do code generation and verification. Again, because Isabelle is a very general system, we can also deal with like C code, for instance. And finally, putting all of this together into a certification document to show that the AMB satisfies its safety properties. Great, so this work is sponsored by the Engineering and Physical Sciences Research Council, my fellowship project Sci-Fi Assure, there's details there, and also the Assuring Autonomy Programme. And we're very grateful for the funding that these two programs have provided to us. And then we've got some references, and happy to take any questions.